Hello everyone and welcome to the Open GIS workshop in Medical Geography. This workshop was developed by the Digital Epidemiology Laboratory at the University of Cincinnati. My name is Santiago Escobar. I am a graduate student at the Department of Geography of the University of Cincinnati, and I will be joining you as an instructor in this workshop. In the introductory video to the workshop, we discussed what geographical information systems are. We introduced the free and open source software QGIS, how to download and install it, interact with its interface, open a layer, add plugins, and navigate a project. In this first session of the workshop, we will introduce the concept of epidemiology and medical geography. We will have a more detailed discussion about the uses and functionalities of GIS, and we will familiarize ourselves with the data formats present inside of GIS and how to open them using QGIS. In the first session of this workshop, we will present the basic concepts and questions of medical geography and introduce the participants to the basic concepts and operations of geographical information systems. The participants will be familiarized with some of the available GIS softwares in the market and their hardware requirements. We will also learn the general data types and formats used inside of GIS, familiarize the participants with the interface of the open source GIS package QGIS, learn how to display the general data formats inside of QGIS, and learn how to display XY coordinate data as points using QGIS. To start defining medical geography, let's first look at its smaller discipline, epidemiology. We can define epidemiology as the study of patterns, causes, and effects of health-related diseases or events within populations. Epidemiologists collect and analyze data from various sources to identify risk factors, trends, and patterns of diseases, injuries, and other health issues, and in turn propose public health interventions targeted towards the control of the observed events. Three main variables need to be analyzed in order to make inferences about the nature of a health-related disease or event. Which population is being affected? Does the event exhibit any temporal trends? And does the event exhibit any spatial trends? Medical geography and epidemiology are closely related fields that both focus on the understanding of the distribution and determinants of health-related events. However, while epidemiology primarily focuses on the examining the disease patterns and health events within populations, medical geography takes a spatial perspective to explore how geographic factors influence health outcome and health services. Location, direction, place, and spatial variations are factors that are analyzed to understand the spatial distribution of health-related events, while posing questions about the influence of both social and environmental factors on the distribution of those events. In medical geography, individual health is understood as the result of the interaction between multiple variables, such as the socioeconomic status in which an individual lives, the physical environment in which he is located, the quality of his infrastructure he has access to, and the health observed in its environment. Other factors, such as individual health behaviors and the accessibility to healthcare present inside of its community, also plays a role. Medical geographers pose questions about the influence of a particular environment on health, the effect of human activity on health on different locations, the spatial patterns followed by disease dispersal, and how does the interaction between population and environment influence the community health. These are technical questions that come with methodological challenges, as we need to have appropriate data for analysis methodologies to make inferences about the processes operating behind the patterns we can observe in space. To solve these methodological challenges, medical geographers make use of different tools, such as geographic information systems, usually referred to by the acronym GIS. These are tools created for storing, analyzing, and managing spatial data and associated attributes. GIS uses advanced analytical tools to explore at a scientific level the spatial relationships, patterns, and processes of cultural, biological, demographic, economic, geographic, and physical phenomena. Among the components of GIS, we can count the data stored and analyzed, the software used to process the information, the hardware used to run the software, and the human component of the people both gathering and manipulating the data. As we have already discussed in the introductory video, GIS uses layers of features to represent reality. By conceptualizing real-world entities into abstract geometrical entities that are linked to corresponding attributes. Each attribute is an individual variable with information corresponding to the properties intrinsic to the features. These features are stored in separate collections of files called map layers. They offer the advantage of being reused easily, assembled into any number of map compositions and overlaid for analysis. A perfect example for the usage of GIS in medical geography was presented during the 1854 cholera outbreak in London. Dr. John Snow, without having access to microscope or any other device, identified a causal relationship between the location of the Broad Street water pump and the spatial distribution of mortality cases of cholera. By overlaying each death, represented as a dot, over the city's map, he noticed that the reported deaths were especially clustered around the water pump located in Broad Street. He did not have any information about the kind of pathogen operating behind this disease, but by observing the spatial pattern exhibited by the disease, he was able to theorize about the processes operating behind its spread, identifying the disease as waterborne, proposing to the city's authorities the temporary closure of the water pump, and corroborating how deaths stopped as soon as the consumption of water from the identified water pump stopped. Geographical information systems make this kind of tasks simpler by providing data collection, storage, and analysis capabilities that were not available during Dr. Snow's time, making this kind of work more efficient and providing the possibility to answer novel research questions. In the Digital Epidemiology Lab at the University of Cincinnati, we use GIS to analyze spatial data of health-related issues. We have focused on various research topics, such as the opioid abuse epidemic in the US, the HIV epidemic in Africa, the COVID-19 pandemic at world level, and chronic diseases and healthcare equity inside of the US. We focus on regional health by establishing collaborations with local health departments inside and outside of the US to protect and improve community health, prevent and control the spread of diseases, promote and support healthy behaviors, and establish emergency preparation and response strategies. We also focus on global health by analyzing problems that transcend national borders, reaching a global impact and having economical and political consequences. Even though several different licensed GIS packages exist in the market, in this workshop we will focus on the free and open source package QGIS. As we have already discussed its history and capabilities in the introductory video for this workshop, we will simply remind that QGIS can be run on Linux, Unix, Mac OS X, Windows, and Android, and support numerous vector, raster, and database formats and functionalities. QGIS provides a continuously growing number of capabilities provided by core functions and plugins, allowing users to visualize, manage, edit, analyze data, and compose printable maps. QGIS is a free and open source software. This means that users don't have to pay for a license and are capable of inspecting, modifying, and enhancing the source code for the package. By having access to the source code, users with programming skills can improve the program by adding features to it or fixing parts that do not work correctly on the current version. Some of the advantages offered by QGIS by being an open source software is the user's control and personalization, the existence of vast training materials developed for and by the community, a secure environment not owned by private companies, increased software stability, and constant community interaction in the form of support blogs, development groups, and constant updates and packages developed for specific needs. To download and install QGIS, search for the official webpage using your user search engine, or alternatively, go to the URL shown in the description below. Select the version you wish to install as well as your operating system. Download the installation files and start the setup wizard following the instructions that will pop up on your screen. In the introductory video for this workshop, we have provided a complete installation guide. You will be able to find the link to this video in the description below. To open QGIS for the first time, go to the desktop or start menu shortcuts and click the QGIS desktop icon. You will be taken to the start interface of the software. Click on New Empty Project if you wish to start a new project. Along with the Project tab, you will get a News tab for QGIS, including the latest version of the package, updates made, bugs fixed, collaborations, etc. If you have previously used QGIS and have available projects, they will be displayed on the Recent Projects tab. QGIS projects are composed by .qgc files, and they store the directories for the features used in the project, the coordinate reference system used to represent them, and the displays options chosen for each individual feature of the form of styles. Projects can be shared between users, and as they contain the directories rather than the actual information used inside the projects, they are light in computational weight and can be used to replicate work and styles quite easily. The two main approaches to representing real-world entities as geographical features to be consumed inside of GIS packages are characterized by a segmentation of discrete feature classes and features inside of each class, or by the representation of a continuous variable surface composed of grids with assigned value or magnitude. As shown in the image below, on the first approach, we would represent a river, road, and building by manually tracing the outline and assigning discrete borders to the extent of the feature, in a process known as digitizing. Whereas, on the second approach, we would represent them by overlaying a grid on top of the terrain and assigning values to each cell corresponding to the values or classes observed in the landscape. Therefore, if the center of a cell happens to fall inside of a river, the class for that cell will be defined as river. Vector data represents geographical entities as discrete points, lines, or polygons by manually tracing the location, path, or outline of an entity to be represented. As previously stated, vector layers depend upon the scale at which they got digitized, as the number of nodes used to represent a feature will vary greatly when traced at different scales from the source entity. By adding additional nodes, the resolution at which a feature can be displayed at lower scales can represent the shape of the feature more adequately. Vector data is represented by three basic geometries with intrinsic properties to them. Points, representing no dimensions but an absolute location. Primes, representing one dimension, which is length. And polygons, representing two dimensions, the feature's perimeter and area. It is important to note that polygons, as the only two-dimensional feature of the basic geometry types, are the only ones capable of containing other features, as shown in the image below. Point data is more often used to represent non-adjacent features and to represent discrete data points, such as hospitals, schools, or banks. They do not have any dimension, therefore they cannot be used to measure length nor area, only the absolute location of a feature. Depending on the scale and the purpose of its representation, all the examples provided might as well be represented using polygons to account for their area besides their absolute location. To display point data inside of QGIS, select the Open Data Source Manager button or click Ctrl plus L. Inside of the Data Source Manager, select Vector on the menu to the right and select the source for the file, which will be the source where you have stored inside of your computer. And now simply click on OK. In this example, we will open a map layer containing information on operational health facilities in Zambia. We will go to the Data Source Manager and make sure that we have selected the Vector option. Now we will go to the Source tab and we will select the source where we have stored our information. This will be variable depending upon the user. Once you click these three dots, you will get a Windows Explorer window inside of which you can go to whenever you have stored the folder GIS underscore files. Inside of that folder, you will find Zambia underscore data. Navigate to that folder, and once inside of the folder, look for health underscore facilities.shp. Be sure that you are using the .shp extension, as all of the other files provided are only auxiliary to the actual shapefile we will be using. Go ahead and click on Open, and once you have selected your data, go ahead and click Add. Your data will be automatically displayed on a white background. Thanks to the coordinate reference system, any layer you open will be displayed on the adequate absolute position relative to the first layer you open. You will notice that the layer you have added has also been added to the layers pane. From here, you will be able to toggle its visibility on and off, drag and drop, and make other operations. Line or arc data used to represent linear features, such as roads, streams, or power lines. Besides representing the absolute location of a linear feature by using nodes, they only have one dimension, and can therefore only be used to represent length but not area. The most distinctive feature of a line is that they have both a starting and an ending point, giving it directionality, and therefore making it adequate for network analysis. If we wish to represent additional properties of a line, such as its width along the trajectory, we could choose to use a polygon instead. But in doing so, we would lose the directionality intrinsic to this vector geometry. To display line data outside of QGIS, select the Open Data Source Manager button or click Ctrl plus L. Inside the Data Source Manager, select Vector on the menu to the right and select the source from your file, which is the route where you have stored it inside of your computer. In this example, we will open a map layer containing information on Zambia's road network. Once again, we will go to the Open Data Source Manager button and make sure that we have selected the vector option. Inside of the Source tab, we will navigate to these three dots, and inside the folder Zambia underscore data, we will navigate to sam underscore roads.shp. Once you have selected your data, go ahead and click Open, and with the source already provided, click on the Add button. You will see that a feature containing information on the road network in Zambia has been added to the blank white canvas. Thanks to the coordinate reference system, any new layers you add will be displayed in the same place they are supposed to relative to the location of the features you have already provided. You will also note how the new features have been added to the layers pane. From here, you will be able to toggle the visibility on and off and manually drag and drop to change the visualization order of the files you are displaying. Polygons are used to represent areas such as the boundary of a city on a large-scale map, a lake, or a forest. Polygon features are two-dimensional and therefore can be used to measure the area and the perimeter of a geographic feature, and the absolute location provided by the location of the centroid of the polygon. Polygons have the particularity of being the only geometry able to contain another feature. To display polygon data inside of QGIS, select the Open Data Source Manager button, or click Ctrl plus L. Inside the Data Source Manager, select Vector on the menu to the right and select the source for the file you want to open, which is the route where you have stored it inside of your computer. In this example, we will open a map layer containing information on Zambia's district. Once again, we will navigate to the Open Data Source Manager, make sure we have selected the vector option, and navigate to these three dots inside of the Source tab. We will scroll until we find the district.shp file. We will go ahead and click on Open, and once we have established the source for our information, we will go ahead and click on Add. The information will be displayed on a blank white canvas. Thanks to the coordinate reference system, any other map layers that are loaded into the project will be automatically displayed on their absolute location relative to the features we have already represented. And as in the previous option, you will see that you have the option to manually turn on and off the visibility of a layer and change the rendering order for the layers. One of the main advantages offered by vector files is the possibility to store data associated to the geometry by using unique numeric identifiers that maintain the relationship between the variable and the geometry to which they belong. Each vector feature can contain any number of attributes. Simply put, we can define attributes as known spatial information about a geographic feature. As previously mentioned, they are usually stored in a table and linked to an unique identifier. Example of attributes could include the recorded temperature of altitude at a single point, the length or flow volume of a line, and area, land cover type, or number of habitats for a polygon. We will use the district layer we had already loaded on the previous exercise to exemplify the data geometry relationship. Inside of the Layers pane, navigate to the layer whose attribute table you are interested in visualizing and right-click on it. Inside of the pop-up menu, click on Open Attribute Table and the attribute table for the features you are visualizing will be displayed. You will note that if you click one of the entries inside of the attribute table, one of the districts will be highlighted. This corresponds to the data geometry relationship. So each of the individual attributes we are visualizing in this table corresponds to non-spatial information that is present inside of this boundary. As previously stated, raster data is represented by overlaying a grid on the terrain and assigning values based upon the magnitudes or classes present inside of that cell. Therefore, our rasters contain coordinate information values for each cell, with cell values containing information such as the elevation for that cell, the slope, rainfall, or any other surface value that is spread across the geographical region. Examples of raster files include aerial photography, satellite imagery, spectral imagery, land cover, digital elevation models, amongst others. The main advantage offered by raster data is that continuous data gets represented with a gradient, corresponding to the spatial distribution of the measured variable. In the case of class rasters, classes are represented by integer values, with each unique value representing a different category or class. For instance, a value of 1 to forest, 2 agricultural land, and 3 to urban areas. To display raster data inside of QGIS, select the Open Data Source Manager button or click Ctrl plus L. Inside the Data Source Manager, select Raster on the menu to the right and select the source for your file, which will be the route where you have stored it inside of your computer. In this example, we will present a raster file containing information on the 1854 cholera outbreak in London as mapped by Jon Snow. We'll go to the Data Source Manager and make sure that in this occasion we have selected the raster option in the menu to the left. Now we will navigate to the Source tab, and inside of the Source tab we will go to these three dots and we will navigate to the snow underscore data folder contained inside of GIS underscore files. We will scroll down and select the snow map.tif file, click on open, and once we have established a data source for our raster, we will click on add. We will see that the information has been automatically displayed on a white canvas. You will get the message that we have used a ballpark transformation, meaning that the coordinate reference system of this raster has been actualized to match with the coordinate reference system of the project we had inside of QGIS. If we scroll inwards into the image, we will see that the resolution starts to deteriorate and we will eventually be able to visualize the individual pixels. Geographical information can also be stored as coordinates with associated values by using comma-separated values or CSV files. Two pairs of coordinates, corresponding to longitude and latitude, are needed to represent a point feature. Associated attributes can be included along with the pair of coordinates to represent non-spatial information. In this example, we will be visualizing the information on the water pumps located in the 1854 cholera outbreak as mapped by Dr. Jon Snow using that CSV file containing the XY coordinates of the water pumps. We will navigate to the Open Data Source Manager option and click on the limited text. Under these three dots, we will click on Browse, and this will automatically take us to a Windows File Explorer window. And inside of the folder snow underscore data in GIS underscore file, you will find the file pumps.csv. Go ahead and click on that one and click open. You will see that we have the option to select a file format, which in this case will be a CSV or comma separated value file, and we will define the geometry upon which we will define the points. We have a unique ID for each of the points, we have the x coordinates, and we have the y coordinates. Inside the x field, we will indicate that we have the column called x, and inside the y field, we will indicate that we have the column called y. If your columns were to be named something else, you need to find the equivalence to an xy Cartesian plane. Once you have established the geometry definition for this layer, you will be sure that you are using an adequate coordinate reference system equivalent to the ones your coordinates are written in, which in this case is WGS 84. Once we have considered all of that information, we will click on Add, we will click on OK in this menu, and as we can see, the water pumps have been displayed in the place where they would be inside of the map. Thank you everyone for attending and listening to the OpenGIS workshop in medical geography developed by the Digital Epidemiology Laboratory at the University of Cincinnati. Please continue with us for the second session of the GIS workshop.